Welcome! In this session, we're tackling problem number 2153, titled Destroy Sequential Targets. This problem challenges us to carefully analyze and implement an optimal solution for sequentially destroying targets based on given constraints. We're excited to dive in and explore the approaches to solve this interesting problem. Let's get started. In this problem, you're given a zero-indexed array nums, which represents targets positioned on a number line, and an integer space. You also have a machine that can destroy targets sequentially. A sequence of targets is considered sequential if, for every pair of adjacent targets in the sequence, the difference between them is exactly equal to space. Your task is to choose a target X from nums as the starting point. Once the starting target X is chosen, the machine will destroy X and all subsequent targets that form a valid sequence, each separated by space. The goal is to determine the smallest starting target X that results in the maximum number of destroyed targets. The expected output is an integer, which represents the smallest starting target X that destroys the maximum number of targets. Let's look at an example to understand this better. Suppose the input is nums equals 3, 7, 8, 1, 1, 5, and space equals 2. For X equals 3, the sequence consists of just 3, meaning only one target is destroyed. Similarly, for X equals 7 or X equals 8, the sequences are 7 and 8, respectively, each with only one target destroyed. However, if we choose X equals 1, the sequence becomes 1, 1, 5. Here, 3 targets are destroyed, which is more than any other starting point. Therefore, the smallest X that maximizes the number of destroyed targets is 1. To further clarify, the maximum number of destroyed targets in this case is 3. And the smallest X that achieves this is 1. Now consider another example where nums equals 4, 10, 6, 14, 2, and space equals 4. Starting from X equals 4, the sequence is 4, destroying only one target. Similarly, starting from X equals 6 or X equals 14 results in sequences that destroy just one target each. If we choose X equals 10, the sequence becomes 10, 14, destroying two targets. However, starting from X equals 2 creates the sequence 2, 6, 10, 14, which destroys 4 targets. Since 4 is the maximum number of destroyed targets, and 2 is the smallest starting point to achieve this, the output is 2. Now, let's examine a third example. If nums equals 1, 3, 5, 7, 9, and space equals 2, selecting X equals 1 creates the sequence 1, 3, 5, 7, 9, which destroys all 5 targets. Since all targets are part of the sequence, this is the maximum number of destroyed targets, and the smallest starting point is 1. Therefore, the output is 1. This example demonstrates how a sequence can include all elements in the array when they are evenly spaced according to the given space value. Finally, there are several edge cases to consider. If nums contains only one number, that number is the answer since no sequence can be formed. If all numbers in nums are unique and space is very large, no sequence longer than 1 can exist. When nums contains duplicates, those duplicates can contribute to the same sequence, potentially increasing the count of destroyed targets. If space is larger than the difference between any two numbers, sequences will be short, often limited to one target. Lastly, since the input size can be as large as 10 to the power of 5, it's important to ensure the solution is efficient enough to handle large arrays within the given constraints. To start, let's consider the brute force approach. The intuition here is straightforward: simulate the process of destroying targets one by one. For each number in the array nums, we treat it as a potential starting point. The goal is to calculate the remainder of every element modulo space and determine how many targets can be destroyed sequentially if we begin with that number. The steps involve iterating through all possible starting points, calculating remainders, and counting how many numbers share the same remainder. Finally, we return the starting point that destroys the maximum number of targets. However, this approach has significant drawbacks. Since we have to iterate through the entire array for every starting number, the time complexity is n squared, which becomes impractical for large inputs. Additionally, it doesn't require extra memory aside from the input, so the space complexity is 1. While simple to understand, this method is inefficient for larger arrays due to its quadratic time complexity. Now, let's explore an optimized approach. The key observation here is that the sequence of destroyed targets is determined by the modulo operation. Specifically, numbers with the same remainder modulo space can be destroyed sequentially if the starting point is chosen correctly. Instead of recalculating remainders for each starting point, we can pre-process the data to group numbers by their remainders, making the process much more efficient. The aha moment comes when we realize that we can use a hash map to count the occurrences of each remainder. With this information, the optimal starting point is simply the smallest number that corresponds to the most frequent remainder. The steps involve creating a hash map to count the frequency of remainders, identifying the most frequent remainder, and selecting the smallest number associated with it. This way, we efficiently determine the best starting point without redundant calculations. Analyzing the complexity of the optimized approach, we see major improvements compared to the brute force method. The time complexity is O(n), since we process each number in the array exactly once. The space complexity is O(k), where k represents the number of unique remainders, which is at most equal to space. This makes the approach highly efficient for large inputs. One advantage of this method is that it eliminates redundant computations by leveraging the pre-processing step with the hash map. Comparing the two methods, the brute force approach is conceptually easier to grasp but computationally expensive, making it unsuitable for larger datasets. On the other hand, the optimized approach significantly reduces time complexity at the cost of using extra space for the hash map. However, this trade-off is well worth it given how much faster the solution becomes. Ultimately, we chose the optimized approach because of its superior efficiency and scalability. By recognizing the role of remainders in determining the sequence of destroyed targets, this method avoids redundant computations and streamlines the solution process. It's both time-efficient and conceptually elegant, making it well-suited for handling large input sizes while staying within the problem's constraints. This strategy ensures that we achieve the best possible performance without sacrificing clarity or correctness, making it the ideal choice for this problem. To solve this problem, we start by understanding the task. We are given an array of integers, nums, and a positive integer, space. Our goal is to determine the maximum number of targets we can sequentially destroy. A target is considered destroyed if its remainder, when divided by space, matches a specific value. The process is then repeated for consecutive numbers. The first step is to parse the input. We extract the array nums in the integer space, ensuring that nums contains only positive integers and that space is greater than 0, as these are the necessary conditions for valid computation. Next, we compute the remainders. For every element in nums, we calculate its remainder when divided by space using the modulo operator. These remainders are then stored in a frequency map, where the keys are the remainders, ranging from 0 to space 1, and the values represent how many times each remainder appears. This frequency map is critical for identifying the most common remainder later in the process. Once we have the frequency map, we identify the remainder with the highest frequency, as this represents the most targetable remainder. If there are multiple remainders with the same frequency, we select the smallest remainder to maintain consistency. After identifying the target remainder, we simulate the target destruction process. We initialize a counter to track the number of destroyed targets and use a set to keep track of the elements we've already processed. As we iterate through the nums array, we check whether each element's remainder matches the target remainder. If it does, and the element has not been processed yet, we increment the destruction counter and add the element to the processed set. Finally, once the simulation is complete, we return the destruction counter, which represents the maximum number of targets sequentially destroyed. To better understand the logic, let's discuss some key insights. The modulo operation is central to this algorithm, as it allows us to group numbers based on their remainders when divided by space. This grouping forms equivalence classes, which are essential for determining which numbers share the same remainder. The frequency map, implemented as a hash table, enables us to store and retrieve these remainder counts efficiently in constant time. Regarding edge cases, the algorithm handles duplicates naturally since the frequency map counts occurrences of remainders, not unique values. If space is small, the range of possible remainders is limited to 0 through space 1. For larger inputs, the algorithm remains efficient because it processes each number in nums exactly once. Key data structures include the hash table for the frequency map and a set to track processed elements during the simulation. In terms of time complexity, computing remainders takes O(n), traversing the frequency map takes O space, and simulating the destruction process takes O(n). Overall, the algorithm runs in O(n) time, making it highly efficient. Finally, let's analyze the space complexity. The frequency map requires O space memory, as it stores counts for each possible remainder from 0 to space 1. The process set, used to track elements that have already been destroyed, requires O(n) memory in the worst case, where every element in nums is unique. Combining these, the overall space complexity is O(n) plus space. This ensures that the algorithm is not only time efficient but also memory efficient, scaling well with input size. By leveraging these optimized data structures and a linear processing approach, the algorithm effectively solves the problem within practical constraints. This Python implementation solves LeetCode problem number 2153, destroy sequential targets. The objective is to determine the smallest number in nums that can destroy the maximum number of sequential targets, based on remainders modulo space. ### step-by-step explanation. 1. Initialization. We use a counter from the collections module to store the frequency of each remainder when elements in nums are divided by space. Variables max_targets and best_remainder are initialized to track the highest frequency of remainders and the corresponding remainder with the smallest value. 2. Calculate remainder frequencies. We iterate through each number in nums and compute its remainder number % space. The remainder_count dictionary tallies the frequency of each remainder. 3. Determine the best remainder. After calculating the frequencies, we iterate through the remainder_count dictionary. If a remainder's frequency is greater than max_targets, or if the frequency is equal but the remainder itself is smaller, we update max_targets and best_remainder. 4. Find the smallest target. With the best remainder determined, we iterate over nums again to find the smallest number whose remainder matches best_remainder. This ensures we return the smallest number that maximizes the destruction of sequential targets. 5. Return the result. The function returns the smallest number that meets the conditions. ### complexity analysis. Time complexity, O(n), where n is the length of nums. This is because we iterate through nums twice, once to calculate remainder frequencies and once to find the smallest target. Space complexity, O(k), where k is the number of unique remainders, bounded by space. This solution is both efficient and easy to understand, making it a robust choice for solving the problem. In this implementation, we start by importing the necessary utilities and defining the destroy targets method. The method takes an array of integers, nums, and an integer space as its parameters. The goal is to determine the smallest number in the array that allows us to destroy the maximum number of sequential targets based on their remainders when divided by space. To do this, we first create a hash map called RemainderCount, which will store the frequency of each remainder. We also initialize two variables, maxTargets to keep track of the highest frequency of any remainder, and bestRemainder, set to integer.max_value, to store the smallest remainder in case of ties. Next, we iterate through the nums array to calculate the remainder of each number when divided by space. Each remainder is added to the RemainderCount map, incrementing its count if it's already present. This map helps us determine how many numbers share the same remainder. After building the map, we analyze its entries using a for loop to identify the remainder with the highest count. If multiple remainders have the same count, we choose the smallest remainder. This is done by comparing the current remainder and count with our maxTargets and bestRemainder variables. Once we identify the optimal remainder, we proceed to find the smallest number in the array that corresponds to it. To determine the smallest number associated with the best remainder, we loop through the nums array again. For each number, we check if its remainder, when divided by space, matches the best remainder that we identified earlier. If it does, we update the smallest target variable by taking the minimum of its current value in the number. This ensures that by the end of the loop, smallest target holds the smallest number in the array that satisfies the condition. Finally, we return smallest target as the result of the method. This approach ensures that we efficiently compute the desired outcome by leveraging modular arithmetic and a hashmap to optimize the process of finding the most impactful target to destroy. To solve this problem, we start by calculating the remainders when each number in the array is divided by the given space value, and then count how often each remainder appears. Using the example where nums is 3, 7, 8, 10, and space is 3, we initialize an empty counter called remainder_count, along with two variables, max_targets to track the highest occurrence of any remainder, and best_remainder to store the remainder associated with that maximum count. As we loop through the array, we calculate each number modulo 3. For 3, the remainder is 0, so we increment the count for remainder 0. For 7, the remainder is 1, so we increment the count for remainder 1. Similarly, 8 gives a remainder of 2, and 10 gives a remainder of 1 again, bringing the count for remainder 1 up to 2. This results in a final remainder_count of 1, 2, 0, 1, 2, 1. Next, we determine the remainder that corresponds to the largest count. We iterate through the counts. Remainder 0 has a count of 1, so we set max_targets to 1 and best_remainder to 0. Remainder 1 has a count of 2, which is higher, so we update max_targets to 2 and best_remainder to 1. Remainder 2 has a count of 1, which does not change our values. The best_remainder is finalized as 1. Now, with the best_remainder identified as 1, we need to find the smallest number in the array that produces this remainder when divided by space. We initialize smallest_target as infinity and loop through the numbers again. For 3, the remainder is 0, so no update is made. For 7, the remainder is 1, which matches best_remainder, so we update smallest_target to 7. For 8, the remainder is 2, so no update is made. For 10, the remainder is 1, but since 10 is greater than the current smallest_target of 7, we do not update. After completing the loop, the smallest number with the target remainder of 1 is determined to be 7. This becomes our output for this example. In a second example, we use nums as 5, 10, 15, 20, and space as 5. The first step is to calculate remainders and count their occurrences. Here, dividing each number by 5 yields a remainder of 0 for all, so the final remainder_count is 0, 4. Since there is only one unique remainder, the target remainder is immediately determined as 0. Next, we find the smallest number with this remainder. Looping through the numbers, all of them have a remainder of 0, and the smallest is clearly 5. Thus, the output for this case is 5. For the final example, let's analyze nums as 6, 13, 4, 19, 12, with space set to 7. Calculating remainders modulo 7 gives us 6 for both 6 and 13, 4 for both 4 and 12, and 5 for 19. This results in a remainder_count of 6, 2, 5, 1, 4, 2. To determine the target remainder, we compare counts. Remainder 6 has a count of 2, so we set max_targets to 2 and best_remainder to 6. Next, remainder 5 has a count of 1, which does not lead to an update. Remainder 4 also has a count of 2, and since 4 is smaller than 6, we update best_remainder to 4. Now, we find the smallest number with the remainder of 4. For 6 and 13, the remainder is 6, so no updates are made. For 4, the remainder matches, so we update smallest_target to 4. For 19 and 12, the remainders are 5 and 4 respectively, but since 12 is greater than the current smallest_target of 4, no further updates occur. The smallest number with the target remainder of 4 is 4, which serves as our output. Here, we analyze the time complexity of the solution by breaking it into 3 main steps. First, in the counting remainders step, we loop through all elements in the nums array. For each element, we calculate its remainder when divided by space and update the remainder_count dictionary. Both the remainder calculation and dictionary update are constant time operations. Since this loop processes each element in the array exactly once, its time complexity is O, n, where n is the length of nums. Next, in the second step, we identify the best remainder by looping through the entries in remainder_count. The maximum number of unique remainders is equal to space, so this loop runs in O, space, time. Each comparison inside this loop is also a constant time operation. Thus, the complexity of this step is O space. In the third step, we find the smallest target by iterating through the nums array again. For each number, we check if its remainder matches the best underscore remainder and update the smallest underscore target variable as needed. These operations are all O1 for each element, so this step takes O(n) time overall. Now, if we combine the time complexities of all three steps, we have O(n) plus O space plus O(n), which simplifies to O(n) plus space. In the worst case scenario, space can be as large as the maximum value in the nums array. However, in most practical cases, space is much smaller than n, meaning the dominant term is O(n). Therefore, the final time complexity of the solution is O(n). Now, let's examine the space complexity of the solution. The main contributor to the space usage is the remainder underscore count dictionary. This dictionary stores the counts of remainders, and the number of unique remainders is at most space, ranging from 0 to space 1. Thus, the space used by the dictionary is O space. Apart from this, the solution uses a few additional variables such as max underscore targets, best underscore remainder, and smallest underscore target, which only require constant space, or O1. Since the input array nums is not modified and doesn't require extra storage, it doesn't contribute to the space complexity. As a result, the overall space complexity is dominated by the remainder underscore count dictionary, which is O space. To better understand the efficiency of the current solution, let's compare it to a brute force approach. In a naive solution, we would iterate through all pairs of numbers in nums to determine how many numbers can be destroyed sequentially for each possible starting target. This would involve nested loops, leading to a time complexity of O(n) squared. On the other hand, the space complexity of the brute force method would be O1, since it doesn't rely on additional data structures. By contrast, the optimized solution we've analyzed uses modular arithmetic and a dictionary to count remainders, which reduces the time complexity to O(n) plus space, and the space complexity to O space. This makes the current solution far more efficient, especially for large inputs. Let's now consider how the solution performs in different scenarios. In the best case, all numbers in nums have the same remainder when divided by space. Here, the algorithm still processes each element in O(n) time, but the remainder underscore count dictionary will only contain one key. This minimizes memory usage to O1. On average, the time complexity remains O(n) due to the linear scan of nums, while the space complexity depends on the distribution of remainders, making it O space. In the worst case, all numbers in nums have unique remainders modulo space. This maximizes the size of remainder underscore count to O space, but the overall time complexity remains O(n), as it is dominated by the linear scan of the array. To summarize the big O analysis mathematically, the solution processes the nums array multiple times, with each pass contributing O(n) operations. Dictionary operations, such as counting and retrieval, are O1 on average, and the second loop over remainder underscore count is bounded by O space. Combining these observations, the overall time complexity is O(n) plus space, but in most cases, it is dominated by the O(n) term. As for space complexity, it is determined by the size of the remainder underscore count dictionary, which stores at most space unique keys. This results in a space complexity of O space. In this section, let's address some common mistakes that can trip you up in problems like destroy sequential targets. First, be cautious with how your programming language handles the modulo operation. While it calculates the remainder, many assume the result is always positive, which isn't true for negative numbers in certain languages. It's important to verify this behavior in your implementation. Next, edge cases are another common pitfall. Examples include handling empty arrays, arrays with just one element, or scenarios where all elements are multiples of the given space. These cases can lead to runtime errors or incorrect results if overlooked. Efficiency is another critical factor. A brute force approach might seem straightforward, but for large constraints like 10 or more, it can lead to time limit exceeded errors. Always analyze the time complexity in the worst case and optimize your solution. Additionally, be mindful of integer overflow in languages like Java or C++. Operations involving large numbers can exceed the limits of standard integer types, so use data types like long or modular arithmetic to avoid this issue. Finally, resist the urge to overcomplicate your solution. Sometimes, a problem can be solved effectively with simple tools like hash maps rather than using overly complex or unnecessary data structures. Aim for clarity and efficiency in your approach. Now, let's explore some insights that can give you an edge in interviews. Recognizing patterns is a key skill, especially in problems involving modular arithmetic. Grouping numbers based on their remainder when divided by a given space can simplify the problem greatly. Hash maps are invaluable in such scenarios. They allow you to efficiently count occurrences or group elements, which can drastically reduce the time complexity of your solution. Be prepared to explain how you're using hash maps and the trade-offs involved. Speaking of trade-offs, understanding the balance between time and space complexity is crucial. For instance, a hash map solution might require O(n) space but achieves O(n) time complexity, which is often a good trade-off. Testing edge cases is another area interviewers frequently emphasize. For example, when the space is 1, all numbers are equivalent under modulo, or when all numbers in the array are the same. These are unique scenarios you should address in your solution. Lastly, always explain your intuition clearly before diving into the code. Articulating why your approach works and how it scales with different constraints demonstrates a strong grasp of the problem. Additionally, understanding related problems can deepen your knowledge and help you identify common strategies. For example, LeetCode problem 560, subarray sum equals k, focuses on prefix sums and hash maps for efficient counting, which is a recurring pattern. Similarly, LeetCode 525, contiguous array, uses hash maps for modular arithmetic-like logic. LeetCode 974, subarray sums divisible by k, directly applies modular arithmetic and frequency counting techniques. Finally, LeetCode 1010, pairs of songs with total durations divisible by 60, demonstrates how modulo logic can be used effectively within pairs. Alongside these problems, it's also useful to consider alternative approaches. Brute force, for instance, might involve iterating over all elements and checking the desired property for each. While straightforward, this often results in O(n) superscript 2, or worse time complexity, which is impractical for larger inputs. On the other hand, grouping elements using a hash map can optimize the process significantly. By counting occurrences of remainders modulo space, you can achieve a much faster O(n) time complexity, although it does require O(n) space. Understanding these trade-offs and when to apply each method is key to crafting an efficient solution. Now, there are a few more approaches worth noting. Sorting combined with a two-pointers technique can simplify problems that involve searching for pairs or maintaining order-based relationships. However, keep in mind that sorting introduces an O(n) log n pre-processing overhead, so this approach is most useful when the problem inherently benefits from an ordered structure. Another highly effective strategy is the sliding window technique. This is particularly powerful in problems involving contiguous subarrays, as it can reduce the complexity to O(n). However, its applicability depends on the constraints of the problem, such as fixed-length subarrays or specific sum conditions. Each of these approaches highlights the importance of selecting the right tool for the job, balancing pre-processing time with the overall efficiency of your solution. By mastering these techniques, you'll be well equipped to handle a wide range of variations effectively. Thank you for following along. We covered the problem destroy sequential targets and discussed a brute force approach while touching on key considerations like constraints and optimization. Remember, understanding the problem deeply is the first step to crafting efficient solutions. Like, share, and subscribe for more engaging coding content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!